Thank you very much for the introduction, and I thank the organizers for the possibility to talk here. Maybe this. That's it. So first, I would like to define some terminology. So when we have two systems of points, like Q1, Qn, and P1, Pn in any metric space, then we say that one system is a contraction of the other if the pairwise distances between the corresponding points are arranged by this inequality. So so the distances between the Qj points is less than or equal to the distance of the Pi and Pj's. Similarly, if we consider a family or a system of balls, or when we are in the plane, then disks, we say that a family of balls is a contraction of another family of balls if just the centers Q1, Qn is a contraction of the system of the centers of the other family of balls, but the radii of the corresponding balls are the same. So the radii are not changed. They stay R1, R2, and Rn. Only the centers are contracted. In that case, we say that the family of balls is a contraction of the other family. Also, just for convenience, I use the words decrease and increase in the weak sense. So whenever I say decrease, it will mean that something does not increase. And conversely, when I say that something increases, then it will mean that it does not decrease. So there is a general problem to find those functions which are defined on systems of points or configurations of balls, which decrease or increase when we contract the system of points or the system of balls. So of course there are some trivial geometrical quantities, like diameter of the set will decrease when you contract the system, but we look for less obvious things, and such a type of quantity is conjectured by Kneser and Poulsen. So the Kneser-Poulsen conjecture predicts that when some balls in the Euclidean space are contracted, then the volume of their union will decrease. So this is still an open question. It is proved only in the Euclidean plane by Bezdek and Connelly. There are other such type of results. I would especially like to focus on the following two ones. So the first there are several proofs of the first result. It says that if we have two point sets in the Euclidean plane, one of which is a contraction of the other, then the perimeter of the convex hull of the contracted system is less than or equal to the perimeter of the convex hull of the bigger or the expanded system. So this was proved by Sudakov, Alexander. There is also a proof by Capoeiras-Pach. And so if you want to find an n-dimensional analog of this, then you can replace the perimeter of the convex hull in an n-dimensional space by the midwidth, and the same statement is true. I mentioned that Bezdek and Connelly proved that the volume of the union of disks in the Euclidean plane decreases when we contract a system. They also proved a dual statement that if we contract a family of disks, and we take the area of the intersection of the disks, it will increase. So under the contraction, the area of the intersection increases. So these are proved. So both results I mentioned here, I proved for the Euclidean plane, but the existing proofs all work, or they all use very heavily that we are in the Euclidean space. And they are not, so at least for me, it is not clear how these known proofs can be generalized, for example, to the hyperbolic plane. So the goal of my talk here is to find an elementary proof for these two statements. By elementary, I mean that it is essentially computation-free, and it will be a proof which doesn't use the axiom of parallels. So therefore, these synthetic proofs will generalize these statements also to the hyperbolic space and also to some disks which are positioned on a hemisphere. So I'll use this fact proved by Kirsch-Braun and Brehm, and so I will tell you. So what I'll use that if M is one of these constant curvature planes, so it's a hyperbolic plane or a Euclidean plane or a sphere, and we take a finite subset, then and the contraction of this finite subset, so a contractive map from X into the plane, then this can always be extended to a contraction of the whole space, a whole plane into itself. So this is the original theorem of Kirsch-Braun, who proved this for Euclidean spaces of any dimension. Of course, then it is true in the Euclidean plane. So the role of Brehm in this is that, so Brehm proved that for this extending contraction, one can always find a piecewise isometry. By a piecewise isometry, I mean a map where we can subdivide the plane into polygons, maybe or polyhedral parts, so that on each polyhedral part, our map F tilde is an isometry. So this is just an illustration how you can map A, B, C to the contracted set A prime, B prime, C prime by a piecewise isometry. I draw only an image of the isometry on the triangle, on the convex hull. So we should divide the triangle into these polygons, and on each polygon we take an isometry, and then these A prime, B prime, C prime will go to the right places. But so Brehm proved this existence of such a piecewise isometry in a Euclidean space of any dimension, and the role of Akopian and Tarasov is that they observed that the proof of Brehm is in fact an absolute proof. So it works in any of these spaces. So nowhere. So the proof doesn't use anywhere that we are in the Euclidean space. So the proof of Brehm is absolute. I think it's true there. That I will use only in the plane because I deal with yes. So it's true in higher dimensions as well. Okay, so the idea that one can extend some Kneser-Poulsen type results to a hyperbolic plane or the sphere with the help of the central set comes from Gorbowitzky's. So let me sketch, or let me go through quickly some definitions of how the central set is defined. So if we take if K is a compact planar set, and we take a disk which is contained in K, then we say that this disk is maximal in K if we cannot find a bigger disk which contains D but which is contained in K. So in this figure, I draw, just for illustration, the union of three disks. It's this light blue region, and draw some maximal disk, maximal disks in it, or just the boundaries of these disks. So it is clear that when you have a disk which cannot be increased further, then it must have at least 2 points in common with the boundary of the union. In particular, if you look at these vertex points, then such a maximal, so the boundary of a maximal disk should go through two of these 3 points. And this is also true in general, and one can show that when, yeah. Oh, sorry, I forgot to define the central set. Okay, so if you take all maximal disks in a domain and their centers, so here I drew some centers of these disks. So then the locus of the centers of these maximal disks is the central set. So we'll deal in the first part of this talk with the convex hull of the union of some disks. And we'll also use the central set of such a convex hull. So the first observation is that if we take the convex hull, the convex hull of the union of some disks, so it looks like a polygon with rounded corners. And so whenever you have a maximal disk in such a domain, it will be tangent to 2 of the sides of this polygon with rounded shapes. And when we fix the 2 sides to which something is tangent, then the center is moving on a straight line. But since the whole domain is bounded, so the centers will draw a straight line segment. So for any pair of sides of this polygon, we can get at most 1 straight line segment within the central set. And the union of these straight line segments will give a graph, a geometric graph where the edges are segments. So even from this initial picture, one can see that the central set will be a graph. And it can also be shown that this graph is a deformation retract of the whole union, or the whole convex hull, because so if you draw segments that start from a boundary point orthogonally to the boundary and draw this segment until it meets the central set, then along these segments you can deform the whole set onto the central set. And since the convex hull is homotopically trivial, it's contractible, the central set must be contractible, so it is a tree. So the central set is always a tree graph. Okay, so the theorem I would like to show is a slight generalization of the monotonicity of the perimeter of the convex hull of some points, because here the points will be replaced by disks. So if we are either in the hyperbolic plane or in the Euclidean plane or on a hemisphere, and we take some disks and their contractions, then the perimeter of the union of the convex hull of these disks will decrease under the contraction. So that's the theorem I would like to show. So the proof consists of some steps. So the first step is that if we consider a family of disks and their contraction, and we look at just one of the disks. So if this disk is not maximal in the convex hull, like this one, then it can be included or covered by a maximal disk. So any non-maximal disk is contained in a maximal one. And by this Kirsch-Braun-Brehm theorem, the contraction we have between these families of disks can be extended also to a contraction of the system where this maximal disk is added. So under such an extension, this maximal disk will go somewhere here. And it's not difficult to see that if this disk was covered by this maximal disk, then taking their counterparts in the contraction, so this disk will be covered by this disk. So the whole inequality we want to prove becomes sharper if we replace this non-maximal disk with the maximal disk containing it. Because the left-hand side doesn't change and the right-hand side increases. So it's enough to prove this the sharper inequality where this disk is replaced by the maximal disk. So this is the first assumption, first observation, that we may assume that every disk in the expanded family is a maximal disk, which means that its center will be somewhere on the central set. So now we consider a family of disks of this type, and so then all the centers will be on the central set. So now we also know that the central set is a tree, and this tree will have branching points. So some vertices where more than two edges or more than one edges meet, say this one and this one. So around these points we can draw maximal disks, and it can happen that so the maximal disks drawn around these points are not in our family originally, but if they are not there, let's extend our family of disks with these maximal disks. So let's assume that all these disks are also in the family. So again, adding these disks to the family sharpens the inequality we want to prove, because it doesn't change the convex hull of the union of the expanded system, but the convex hull of the union of the contracted system may increase. So the two values go closer to one another. And so once we do this, after this we make an induction on the number of disks we have in this family. And the induction is the following. So of course for one or two disks everything is clear. Now, so the trick is that when you have a tree, it always has a vertex of degree 1. So let's choose a vertex of degree 1 in our tree. And so there will be along this neighboring center. So in the figure, the center neighboring this vertex is here. And let's consider these two disks. And let's label the disk so that this is the nth disk, this is the n minus first disk, and we have all the rest. And here are some notations to complete the proof. So let kj be the whole union, so the convex hull of all the disks. So this is the same for the contracted set. Let L be, kg is just the union of the first j, sorry. And so let L be the convex hull of the union of these two neighboring disks, and L prime the convex hull of the union of their images. And then one can write this sequence of equations that the perimeter of this full convex hull can be decomposed by the fact that the perimeter is so by this inclusion-exclusion formula. So the perimeter of this whole thing will be the perimeter of the yellow, so of the convex hull of these two disks, and plus the perimeter of the disks from 1 up to n-1, so when we omit the last one. And we should subtract the perimeter of the intersection. But so that's an essential corollary of our construction, that the intersection of these two domains is just the n-1st disk. So the perimeter of the intersection is just the perimeter of the n-1. And then we can write that this is greater than or equal to. So the first is greater than or equal to the perimeter of the corresponding first n-1 disks in the contracted system. And so we take the convex hull of their union and the perimeter. So this is by the induction hypothesis. Then we can also use the fact that the perimeter for the last two disks, so the perimeter of the convex hull of the last two disks also decreases under the contraction. So this is greater than or equal to this one. And so dn-1, so there is a dn-1 which is contained in the intersection of, so this should be kn, and so kn prime intersected with l prime. So this perimeter is less than or equal to this perimeter. So if we replace this perimeter with this one, then this inequality will be true. And by an inclusion-exclusion type formula, this is just the perimeter of the union of k prime and l prime. And this perimeter is greater than or equal to the perimeter of the convex hull of this union. It's again a trivial inequality, and it is exactly the perimeter of the convex hull of the contracted system of Bose. Well, so this is the proof of the statement. So maybe I go further. So I would like to show a similar statement, not for the perimeter of the union of the convex hull of Bose, but for the area of the intersection. So for this, the central set is not really a good notion. So what we need is a dual version of the central set. And so one can find out how to define it. So if you do dualize everything. So suppose that we are given a compact panel set K, like this blue domain. Then a disk will be a minimal disk containing K if there is no smaller disk in D, which also contains or covers D. And so looking at a domain, so say a compact domain, we can take all minimal disks that contain this given domain and take the centers of these disks. So this we can call the co-central set of the original domain. And so what is important for us is that if you look at, so if our initial domain is the intersection of some disks, then the co-central set will be again a tree, and that's easy to check. And so among the vertices of this tree, we'll find the vertices the centers of those disks that take part in the intersection. So if we take this intersection of 4 disks, so if you look at a boundary arc, then this whole circle will be a minimal disk, so its center is in the co-central set. And so this is a tree. So if we want to show this second statement that oh, sorry, there shouldn't be this convex hull. This intersection is, of course, convex. So then, so first we can omit or decrease some of our disks. So first we can assume that if a disk is not a minimal disk which contains the intersection, so please omit this convex hull operation, then we can decrease it, and when we decrease, replace it by a minimal disk, the inequality we want to show will become sharper. Similarly, we can add further disks to our disks whose intersection is taken, because if you look at this tree, I mean, so this co-central set, then for every vertex of this tree, there is a minimal disk that contains the intersection, and these minimal disks can be added to the system. And if we add these disks to the system, then the inequality we want to show becomes sharper. And after that we move all the centers of the disks that take part in the intersection to the central set, and we may assume that every vertex of this tree is a center of a circle. We can complete the proof by a similar easy induction as in the case of the convex, as in the case of the perimeter of the convex hull, of the union. So here we introduce these notations. So Kj is the intersection of the first J disk, Kj prime is the intersection of the corresponding disks in the contracted system. We denote by L the difference of these two disks, and L prime the difference of the disks in the contracted system. So in this figure, L is this yellow domain, and there is something corresponding in the contracted system as well, and here is the proof. So the area of the intersection of all the disks. So if we omit from the so this is the last disk which is omitted. So if this disk is omitted, then this yellow domain will be added. And again, by the construction, so when the last disk is omitted from the system, then exactly the difference of the n-first and the nth disks will be added to the system. So this is so the first equality is true. Then we use the induction hypothesis for k n-1 and its contraction, and L and the contraction. So this difference will be less than or equal to the difference of the corresponding areas in the contracted system. Then, so we don't change this one, but increase so Yes. So this inequality is also an obvious inequality, and so this last part is just the area of the intersection of the contracted system. Well, so I think my time is essentially over, and so the proof is also complete, and so this proof is really absolutely elementary, so it works in the hyperbolic plane. So it remains to use this last slide and last chance to thank you for your attention, and I would like to wish happy birthday for our celebrated friends, Endre, Gabor, and Ted. So, thank you.